This learning object is a production of Abu Dhabi Men's College, Center of Excellence for ICT and Learning Technology.
Now we're going to look at some data capture devices that support geographic information systems. What I have here in front of me is a global positioning system, GPS, as most people know it as. Now what we have is a Leica brand. As you can see here, this is Leica. This is basically an antenna which we use together with the data logger. The data logger, actually, we can enter input information. This is basically a receiver, okay, that we use. We call this set a base station. What this means is we set this up over a known point. A known point means the point has an X and Y coordinate on the Earth's surface. This receiver, this system, tracks the satellites in orbit. The Americans have put out more than 20 satellites in orbit. So at any given point in time, when we are using this, we need to pick up a minimum of 4 satellites, okay, which must have good health, meaning that they are clear, there's no obstructions and things like that. This is static. It stays on over this point that we set it up for as long as we are busy surveying in other areas. It locks onto a minimum of 4 satellites. At the same time, what we do is we take another set of this and we put it on our back, or we could put it on the top of a car. This again is the same system, and we can capture data in kinematic mode. Kinematic means stop and go. We can stop 3 seconds, pick up a position by just pressing some of these buttons and moving on that way. So what actually happens is the base captures the 4 satellites. The rover, which we're moving around with, also captures the same 4 satellites. But the base, what happens is the satellite has a clock that's called an atomic clock. The clock in these receivers here is a quartz clock. So there's a big discrepancy in terms of the error. So we use what we call two-way radios. I don't have one with me here now, but the two-way radios transmit the error to the rover. In other words, a correction that needs to be applied. And this correction is what we call the clock bias, which means the difference between the atomic clock and the quartz clock. So the GPS works on that principle. So we capture data with descriptions. We can take this data back to our laboratory, and we can download it on a PC using Leica software. We could refine the accuracy with the software. Once we've done with that, we store it in drawing exchange format, and we export it to the GIS system, ready for map making and creating a database. Another type, GPS is very popular. While I'm there, I'll rather show you another portable GPS device, standalone. Standalone means not high accuracy. This handheld GPS can give you an accuracy of no more than 50 to 60 meters. Okay? The accuracy of this system here is 1 centimeter in position, XY. The height's 2 to 3 centimeters. Okay? I will now move on to the total station. So this is one type of data capture operation one could engage in for GIS development. The total station, this is also not the latest version of the total station, but it still is a total station. It's got about a 5 second accuracy. Distance is normally about 4 to 5 millimeters in accuracy. And basically what this instrument does is it captures directions and distances on the Earth's surface, and from that we can calculate coordinates of any points we wish to capture in any area on the Earth's surface. Once we capture this information, we download it directly into the, using the software, into the computer. We do the calculation, the reductions, X and Y coordinates, and we then save it in drawing exchange format and export it again to the GIS system. Now, what happens is when we capture data like this, remember the Earth is not round. The Earth is three-dimensional. The Earth is a geoid. It bulges at the equator because it's not a perfect sphere. So we have to convert the data from a three-dimensional Earth surface to a two-dimensional plane surface, which is the map, which is what we have here. So the GIS system that we have here is basically abstracting reality, right, and representing it from three-dimension in two-dimension in a plane system within a chosen type of datum. Okay, different parts of the world have different datums that we can use. It's a subject of its own that I would need to engage in at a later stage. Okay, another important data capture method is digitizing, which we can take a paper map and we can digitize that and reproduce it in digital format on the computer, and we can export that to the GIS as well. And we can also use the digital image, and we can digitize that as well to capture certain desired types of data that we require. Again, we can export that to the GIS as well. The last but not least is the photogrammetry and remote sensing. Much of it is beginning to be integrated nowadays. Remote sensing, much of our data seems to come from remote sensing. The US have put out more than 20 satellites in orbit, and we are in a position to acquire continuous data capture 24 hours a day, so we can use that data in our GIS mainly as base data or initial data and refine that. In fact, the accuracies of remote sensing used to be 15 meters previously. Nowadays, the accuracy is down to 5 meters and even 1 meter in some instances, which is more than sufficient for most GIS operations. Photogrammetry, again, very popular. We have a module in GIS where we can take the images or the photographs from the aircraft, which flies at an altitude of roughly 5,000 meters on average. But if the accuracy, a higher order of accuracy is required, then obviously that altitude has to decrease. Now we can take that information to the GIS in the module that we have for photogrammetry, create a map out of it in digital format, and export that to the GIS system. So that's basically an overview of some of the methods that one could use for data capture for GIS. Thank you.